All right, again, now that we are recording, are there any questions, issues, concerns, problems, anything else left over from last week? Okay, let me just make sure nobody else is waiting. Nope, just the two of you. Okay, hopefully the others will be coming in. Well, let me do a little confession time here. I was just so happy toward the end of last week. I was finally getting caught up, and I did get caught up all the printing of stuff that had come in since the first of the term, and I was way, way behind because this term has been absolutely incredibly time consuming. There have been so many things to do with this new banner, so many things to do with just about everything. Uh, and I finally was able to have some time enough to go through and make sure I had all the um, things printed that students had sent me, at least from email. And I was working at that when up popped an email, and this had to be Friday afternoon. I was that close to getting ready to start grading because I just about got everything printed. I was getting ready to start grading. I was so happy to be able to grade, which is not one of my favorite things to do, but I felt so far behind that I thought I finally will be able to get some of these papers graded and things put aside, put things in Blackboard, and put the papers where they belong. When along came an email from the dean that we were required to watch these four presentations from these various um, software providers. What they are, we have gone to this Blackboard Ultra. You'll remember we were in Blackboard before. We went to Blackboard Ultra last spring, and that was a real pain in the neck, and still is. Um, but the state is intervening again, uh, just like they did with the course with the administration system. We were using an old one. It was ancient. I didn't like it, but it was called Alliant, and the state intervened and said, "Nope, everybody will use Blackboard. Banner. Will use Banner." So we had to, and the school started doing it last spring. Certain individuals from the school started learning Banner. They are sharp people. They are IT savvy people, and it took them months to just get a hold of Banner. And Banner wasn't even adequately prepared for us yet. There were some functions they couldn't do, and still can't do. So it's a real huge pain in the neck. Okay, but anyway, we were forced to go to Banner this fall, which of course is the biggest term of the year. Fall term when all the new incoming students come in. Uh, we were virtual, which is the first time we'd ever done a fall virtual. We had to go virtual last spring, and then summer was the first term we had done virtual from the beginning, but that's usually a pretty small term. Okay, not a smaller number of students, and we sort of got our feet wet, and it was hard doing that. But then this fall, not only going virtual, but having to go virtual on Banner, which didn't have all the support we needed. So, but the state decided we had to do it this time. We couldn't wait another term. We had to do it this fall. Well, now the state says we have to all agree on one course management system. We've just gone to this Blackboard Ultra, which has been a pain in the neck to adjust to. And what's more, the school has made it even more of a pain in requiring virtual classes to use the online templates, which don't fit. They don't fit at all. Little things can work okay, but overall, it's just a lousy trying to force a square peg into a round hole. It's been miserable doing that this fall, in addition to everything else. So the state, here we come. I can't tell who it is. Ashton is coming in. So let me get Ashton here. Ashton's here, so we're only missing Brandon. Hopefully he'll be coming in soon. Ashton, I was just griping about all the things happening this term, and I was saying that this finally toward the end of last week, I was finally getting caught up printing off all the materials that had been sent in to me since the beginning of the term. And I was so anxious to look forward to starting grading. That's not my favorite thing to do, but I was really looking forward to grading. So, and getting started on clearing out some of the things in my uh, book, especially a first mini-term class. I'll just give you an idea. Uh, these are things that this class is, or my Monday, Wednesday classes have done. Just a few of those to grade. Some of your materials are right in there, and mark in the book and mark on Blackboard and stuff like that. But I have a first mini term physical science class. I have that many to go. Okay, and this is, I mean, that is a huge pile that I've been trying to get to. I've gotten some of them done here and there, but I was finally thought, boy, Friday afternoon I'll be able to start on this. Well, the dean sent a message, and I was just explaining this. The state has decided everyone in the system has to use the same course management tool. We just changed to Blackboard Ultra from regular Blackboard last spring, and now they're saying we have to change. We have to all agree on the same one. So the state had invited 4 vendors to come in, and they did this the first week in September, I think, somewhere around there. I think they presented to the IT people on a Thursday or Friday, and then presented to faculty on a Tuesday or Wednesday after Labor Day. Um, well, I don't think I was invited to that, but they recorded it all and then said we had to watch these 4 vendors give their spiels. And I don't know if you've ever heard of these salesmen coming in and trying, think used car salesman, just how wonderful this car is, and how, yeah, blah, blah, blah. Well, that's what we had to listen to. Every one of them went more than an hour and a half, and we had to listen to 4 of them. That's more than 6 hours of having to listen to all this blah, blah, blah. It was one of the most boring, more than 6 hours I've ever had to waste in my life, and we were forced to do it because we had to submit a whatever they call it. It's sort of a survey question, answer 10 or 12 questions on each one of them. And it was awful. It ate up my entire weekend because I had other things to do this weekend. And so I finally finished it last night after 10 o'clock. At 10, I stopped the last one. It still had a few minutes to go, but I was just so sick of listening to them talk that I stopped it and then did my evaluations and shut down and went to bed. Didn't get a single paper graded this weekend, and that's what I had planned to be doing this weekend. So that's my sad song. Didn't you hear the violin music in the background? So anyway, that's over with. I don't know what they'll come up with next, but I'm sure they'll try to find something that can keep us from doing our jobs. Okay, I'm sorry, I'm sort of on a rant right now. Okay, any questions, concerns, problems? That was my sad song. You got any of your own? Okay, if not, yes, yes. Okay. Right, right. That was the top thing I have here was your research paper. Okay, that was the first thing I was going to grade before I got that email from the dean, and oh, it just aggravated me. No, I'm grading everything backward now. This thing about the points there, that was put in by somebody. I don't know if Blackboard did it itself or whoever made up these silly templates that we're having to follow. Uh, I don't know if you were a student here before. Blackboard probably looked fairly different to you from what it looks this term, because they're forcing, since we're virtual classes, they decided, well, let's make all virtual classes um, have to follow the same template that the online classes follow. Well, they're different night and day. They're different animals, and they don't fit well. And so they took these templates and basically are forcing us to use them. And they, either the people who made up the templates put the points in there, or Blackboard put them in. I don't know. Okay, I don't know who put them in there, but they're meaningless. Okay, now things that you've turned in so far, like the syllabus agreement, research paper topic, and if you've turned in any homework problems over the first 5 weeks now, yeah, those, when they're, all I do is acknowledge that I received them. And that acknowledgement is done by, it's 0 out of 0 points. I wish they didn't say that. I wish we could just post that we received them. But no, they have to have points there. And since there's no points for doing that, it's 0 out of 0. So that's what you're seeing there. Now, some of them are posted and some of them aren't. Like I said, I have not that many from this class. I have Ashton's research paper, and then the rest of them are from my Cal 3 class, or possibly my of this stack here from the differential equations class. Okay, so those are the things I haven't posted so far, haven't graded or posted. But then I think, okay, we'll get to that. No, yeah, we'll get to that in just a little bit. But that's what I'm trying to grade, and hopefully this afternoon they won't give me any other silly waste of time exercise to do, and I can grade papers, because I do have from 4 to 6 this evening, unless I have students who have signed up for virtual advising. I have from 4 to 6 this afternoon to maybe get back to grading. But then too, I still got to go back and check to see if any new emails came in this weekend, and also if anyone posted anything on Blackboard messages or in the assignments. I went through this class. I didn't see anything new posts from any of you, but I may have them from other classes. So that's the plan for me the rest of the day, is once my 3 classes are over with, then hopefully get started on printing out anything that's left and then start the grading. Now, when I'll get to post them on Blackboard, I don't know, but I will as soon as I can. I get fussed at a lot for working in the evening after I eat supper, but I'm planning to come back up and work and get those done after, continue that after supper tonight. Then tomorrow, 8:30 in the morning until 5:45 in the afternoon, I'm in class solid. 2 15-minute breaks and 1 30-minute break when I try to cram down lunch. That's all I got tomorrow. So Wednesday morning I'll have some more time. Hopefully before we meet again, most of the grading will be caught up, and also maybe even put in Blackboard. I hope so. Sorry, that's a long answer to a fairly simple question, but did that answer what you were asking?
Yes, sir.
Okay. All right. Glad to. All right. Any other questions, issues, concerns before we get started with the calculus today? Okay. All right. As I was mentioning before, we're in Chapter 5, Integration, 5.7. I've decided this will be the last section we do before we move to Chapter 7. Okay, we skipped Chapter 6, it's differential equations, that's another course. Okay, so this will be the last section we'll do. And we'll talk a little bit more about that. If we finish this today, and I've been talking too much now, so we may not, but if we do finish this section today, I will post your test out there on Blackboard. Now let me tell you where I'll post it. I'm going to try to post it in 2 places. One place is under right now it says week 6 assessment. But when I go to post your test there, I'm going to say test, let's see, chapter 5 test, and I'll put in parentheses test 1. So I'll post it there under that. Right now it says week 6 assessment. I'm going to change the title to be chapter 5 test, test 1. Okay, and then I'll also post it under Blackboard messages because some of you are used to getting your tests there. So I'll put them in both places so you will have access to it if we finish this section today. And I'll talk more about that as we move on. So any questions about that or anything else? All right, what we are in chapter 5, integration 5.7, the natural logarithmic function integration. And we had done examples 1 through 3 on page 356 to 357. We're just getting ready to start example 4. So I'm going to write it down now. I think I'm going to have to get it in my lap because it's on the opposite page and it's hard to read from the side like that. So here we go. That sorry box is in the way. I'll have to start down here. Here's the A part of example 4. The integral of 3x squared plus 1 over x cubed plus x dx. Okay, now let me go through a couple of things I don't think they've done a really good job of doing yet. So let me mention them now because they're going to be important later. Number one, what this is called is a rational expression. And you had that back in pre-calculus algebra, I'm pretty sure. And what do we mean by rational expression? Anyone have an idea? Do you remember that? What's the first 5 letters of rational? R-A-T-I-O, ratio. What does that mean? Ratio is a comparison of two entities in a division sense. So the definition for a rational expression, the way we use it in pre-calculus algebra and in calculus, a rational expression is a ratio of two polynomials. The numerator is a polynomial, the denominator is a polynomial. Okay, there's step 1. Number 2, in order to do something with this, we have to make sure that it sort of looks like a fractional form, right? It's a ratio, which a fraction is a ratio of two numbers. This is a rational expression, a ratio of two polynomials. The numerator polynomial has to be a lower degree than the denominator polynomial. Numerator up here is degree 2, denominator degree 3. Yes, we can proceed. If that were not the case, the first thing we do is division of polynomials. Okay, that's what we would do first. This one, we don't have to do that. The degree of the numerator is less than the degree of the denominator. All right, now, in a later life, we'll have another way to do this kind of problem, but what we've got now works out quite nicely because what we're doing, this chapter has been on integration, and the main thing we've been using the tool to integrate has been substitution. So what usually you use to substitute is the most complicated element of your of the integrand, and that would be in this case the denominator. So that's what we're going to let u equal the x cubed plus x. Okay, what always follows your let. then du is equal to what?
3x squared plus 1.
3x squared plus 1. One more little thing.
Dx.
Dx. Excellent. And now we look up here and say, lo and behold, that's exactly what we've got here. So we can directly do our substitution now. This integral now becomes, the numerator is du, and the denominator is u. Okay? And what is the antiderivative of du over u? That's what we're doing in this section. What is the name of it? The natural logarithmic function integration. That's what it is. That's log absolute value of u plus c, because of course this is the indefinite integral. Now the last step is just plug in what u is, or u are, okay? And that would be the log, the natural log of absolute value x cubed plus x plus c. That's your answer. That's all you can do with it, okay? Basically, you could do a few more little things, but they really wouldn't make it any simpler. We need to keep the absolute value bars here because x cubed can be negative, x can be negative. We can't take the log of a negative number, so you have to have the absolute values there. Now, what's more, you can't take the log of 0, so I can tell you right now, x cannot equal 0, because that would make that thing in there 0. And if x can't be 0, then you're almost guaranteed that x has to be a positive number, because you usually don't have answers that have discontinuities in them. So in that sense, you could almost say, the book doesn't, that would be the log of parentheses x cubed plus x plus c, and then off to the side say x greater than 0. Can't be greater than or equal to, greater than. This doesn't say it, it leaves it just like that. The log of absolute value x cubed plus x plus c. Okay, let's do the B one. I think we've got room down here. Let's try it. What is the integral of secant squared x excuse me, over tangent x dx? Okay. Now, in most times when I would have a problem like that, my immediate reaction would say, let's get everything in terms of sines and cosines. Okay? Except we are integrating. And since we're integrating, I first want to say, well, is any part of this a derivative of the other part? And I think you see the answer then. This is just like this one here. Believe it or not, the denominator is a more complicated thing here. So let's do our u substitution. Let u equal the tangent of x. And what follows the let is always a then. Du is equal to, does anyone remember what the derivative of tangent is? Now, if you don't, shame, no, if you don't, go to the front inside cover of your text. Okay, if you got your books handy, the first page in your text, the first loosely page, is a cardstock test page, and on that, the more than the top half is basic differentiation rules, and the bottom little less than half is the basic integration formulas. And in that you have your trig functions, and the tangent is number 15 in the top part. d by dx of tangent u is secant squared u du. Well, we're going to use x's here. Secant squared x uh, dx. And that comes in pretty handy because sure enough, yuck, I didn't even touch the page and it just put a mark across there. Let me see if I can get my eraser to come on. Okay, and then my pen to come back. So then du is equal to secant squared x dx. Now, I don't know if you just saw me writing the secant. There, I didn't even touch the page, a line went across it. But then when I went to put the, the line in E, it wouldn't write. Okay, so sometimes it writes when you don't want it to. You don't even touch the board. Other times when you're trying to write, it decides it won't. So I don't know. This Wacom, I don't know. It's a little, I'm glad to have it, but it can be a pain. So what do we have here? Secant squared x dx is exactly your numerator here, and that's your u. So this is the integral of du over u. And please tell me you can tell me what that is.
ln
That's
value of u.
perfect, just like it was before, plus c. Excellent, excellent, excellent. And what do you do with that then?
Secant squared x
Okay, no, you plug the u in.
dx.
The u is tangent x, right? And you have to keep the absolute value bars because tangent is sometimes negative and sometimes positive. It's also sometimes zero, okay? So x cannot equal zero. So since x can't equal zero, because the tangent of zero is zero and you can't take the log of zero, in this problem also, I would have preferred they write the answer as log of tangent x in parentheses plus c, and then to the side say x is between 0 and pi halves. Okay, now why pi halves? Because tangent is undefined at pi halves. It goes to positive infinity. So therefore it's the log is undefined when x is equal to 0. The tangent is undefined when x equal pi halves. So in my mind, the better answer here would be log of parentheses tangent x plus c, with x is less than, no, 0 is less than x unless x is less than pi halves. No equals to in that on either end of that. But the book doesn't do that. Okay, and we'll leave it alone and leave it just like they did. All right, that sort of fills the page. Any questions on these? Oh, here comes Brandon. Ding, ding, ding. Perfect attendance today again. Way to go, team. It's going to take me just a minute to set down my stuff so I can get Brandon marked in my grade book. Way to go, folks. Perfect attendance. It's a solid week and a half. In fact, I think there's only been one day since the first of the term that there's been somebody absent, okay? And so way to go. Y'all are a great class. You're here, and that's great. Um, One of the presentations that we had on Blackboard, we have to put attendance in on Blackboard now, and Blackboard always assigns grades for attendance, which we don't do grading for attendance. That's not what we do, but we still have to put the attendance in just because the administration is a little anal retentive that way. So we have to put them in. So if you see a grade for attendance somewhere there, it means nothing, okay? For all of you, it's going to be quite good, okay, because you have been here. But in some of my other classes, some of the students are really panicking. What does this mean? You know, I said, it means absolutely nothing, okay? So you, if you do see that, pay no attention to it. I have to put attendance in there, and this class is so easy. Present, 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 present. Okay, most of the time that's all there is, and it's just an easy thing to do. Some of my big classes were Not many people are absent, but when there are some, then I have to be really careful I get the absences in the right places. But it's just another thing that they make us do, which has basically no meaning whatsoever. All right, any other questions on these two? Brandon, by the way, we're in Chapter 5, Integration, Section 5.7, the natural logarithmic function integration, and we're doing example 4, which is not on the slide set, so I'm doing them on the whiteboard. We've just done A and B here. Getting ready to do C. Does anyone need this up here a little bit longer? All right, if not, I'm going to clear this drawing so I can get C in here. And here's C, and because that sorry rectangle is in the way up there, I got to come down a little bit. Here we have x plus 1 is the numerator over x squared plus 2x. And by the way, the B example was not a rational function. It was a ratio, but it was a ratio of two trigonometric functions, so they don't follow the same rules as polynomial functions. Okay, this though, going back to a polynomial function, this is a rational function. The degree of the numerator is less than the degree of the denominator. We can proceed. How do you think you would go?
Let u equal x squared plus 2x.
Perfect. Let u equal x squared, see the pen's just not writing, plus 2x. Perfect. Then du is equal to what?
2x plus 2.
Perfect. 2x plus 2. Well, we don't have a 2x plus 2 in the numerator here, but we have something pretty close to it. Oh, you left off, or I left off the dx. You can factor out a 2 here. 2 times x plus 1 dx. And sure enough, this is what we've got in the numerator here. If we can just get rid of that 2, which we'll do by dividing away the 2's here. Now this becomes du over 2. So when I write this down up here, I'm going to put du in the numerator, but I need that over 2, but since it's a constant, I'll bring that 1/2 to the outside. And then our denominator, x squared plus 2x, is exactly u, du over u. And I think you probably got an understanding now of what that antiderivative is. Anybody?
ln value of u
Yeah,
plus c.
absolute value of u plus c. Now, there's a little bit of me that wants to leave off the plus c for now. I'm going to go on and write it because you said it, but I'm going to probably change that in a little bit. All we do now is plug in what u is. U is that, so that would be 1/2 I'll put the brackets here again, log of absolute value of x squared plus 2x plus c. Now, the reason I sort of want to leave the c off here, right now that's being multiplied by that. So what I'm going to do is say I'm not going to use that same c that was here. I'm going to use half of that c, which is still a constant. So what I'm going to do, and this probably seems like it's a sleight of hand, and it kind of is, but let's just write it this way. Okay, 1/2 the log of absolute value x squared plus 2x plus c. Now, again, x can't be negative because there are a few places where 2x will be greater than the absolute value of 2x is greater than x squared. It's just a pretty small region there, but that would make this negative. But guess what? x can't be 0 either because you can't take the log of 0. So in my mind, it would be better to say x greater than 0, okay, and then leave off the absolute value bars, just put parentheses. Now another thing you can do, and you don't have to, you could also say this. This is one of the principles or rules of properties of logarithms. That's the same as the log of the absolute value of x squared plus 2x to the 1/2 power. That's a property of logarithm. You can do that plus c. That's the new c, okay? Half of that original c up there. And you could have written this as the log of the square root of x squared plus 2x. But again, you still need that absolute value bar in here. And here's why. You can't take the log of the square root of a negative number either. So you do need the absolute value in there. Unless, of course, you said on the side over here, comma, x is greater than 0. Can't be greater than or equal to, greater than 0. Then you could write it in any form you wanted to with parentheses here, parentheses there, or parentheses there, or just leave off the symbols altogether. Square root of x squared plus 2x. That would be a legitimate answer. They leave it in the form we have right here. No, they don't. They leave it in the form we have right there. They don't even do the principles of property of logarithm. All right, now that took most of the page. Any questions on that before we move to the D part? Okay, let's go to D. Uh-oh. Here we have the integral of 1 over 3x plus 2 dx. Now how are we going to do that one? Do you want to do a u substitution? You want to try it brute force?
Let u equal
I like it.
3x
Okay,
plus 2.
let u equal 3x plus 2. Then du is equal to what?
3
3 what?
dx.
3dx. Perfect. Well, we don't have a 3dx. We have a 1dx. So if we take this and divide it by 3, we also have to divide this side by 3. And that then, when we write this as a du up here, rather than putting the 3 over here, we'll bring it on the outside, and that would be over u. And there's that same form we've seen repeatedly, and what would that be?
ln absolute value of 3x plus 2.
Yeah, okay, he's jumping right to the end. 3x plus 2. One more little thing.
Plus c.
Plus c. Perfect. And this time we'll have the c that incorporates the 1/3. Now, again, and the book probably leaves it just like that, you could, not necessary, but you could write that as the log of, now, you still need the absolute value bars. 3x plus 2 to the 1/3 power plus c. Or you could have written that as the ln of, now, here you can go either way. The cube root of 3x plus 2. But you still need absolute value bars. But the thing is, you could put the absolute values on the outside, or you could put it on the inside. Either one because you can take the square root, the cube root of a negative number. That's perfectly fine. It's only even roots you can't take the root of a even number, of a negative number, but an odd root you can. But you can't have a a negative number here you take the log of. So you still do need the absolute value bars. Probably better to put them on the outside. But then too, you needed to say at some point here, x cannot equal negative 2/3, because that would make this 0. The cube root of 0 is 0. You can't take the log of 0. So I think it would be better in my mind to say x has to be greater than negative 2/3. And if you said that, then you can leave off the absolute values and leave it like this. If you don't say that, you do need the absolute value somewhere. The book leaves it just like this, and we'll be happy to leave it like that. That's all you have to do. But just for future reference, and they do mention this at the bottom of the page, you could have written it that way. They write this form here, the one up under this one right here. And they put the absolute value bars. No, I'm sorry. Yeah, wait. I'm sorry, I said it wrong. In the book, they wrote their answer this way. They left it like this. And then at the bottom of the page, they said, or you could have done this, and that would have been fine too. They didn't rewrite it in radical form, but you don't have to. Okay. Now, any questions on those before we go? I probably went a little overboard telling all these other things, but later in calculus, you will need to always keep in mind what your domain is. Okay. Now, if there's no more questions on this, I'm going back to the, if I can ever find my cursor. Does anyone, there it goes. There it is. Okay. Let's go back to our PowerPoint. And this is in 5.7. Okay. And go back to current slide. And we have to step through example 1, which we did last time. Now, and here is the top of page 358. I'm going to get this thing out of my lap because it's heavy and it's hot. Integrals to which the log rule can be applied often appear in disguised form. Okay, they're wearing masks. Never mind, I just made that up. For instance, when a rational function has a numerator of degree, this is what I was talking about before, greater than or even equal to the degree of the denominator, you first have to do division. And that may reveal a form that you can apply the log rule to. Okay? And example 5 is like that. So let's go straight to example 5. Now in this case, don't try to do a U substitution yet, because this is a rational expression and the ratio of the leading terms is, well, the degree of the numerator is equal to the degree of the denominator. To do the rules we've been doing, you have to have that less. So what we have to do is come over here to the side and do a long division. The reason you have to do long division, synthetic division won't work with the x squared. Okay, if that was x plus 1, fine, you could do synthetic division. Not here. So what we do, we divide the x squared. Now, I like to do this. It's not required, but I like to do it. Plus 0x plus 1. I like to put that in there because up here you've got to put it in there. And I like to go on and put it in the outside as well. That helps me, keeps me from making some dumb mistakes. And that's going into the numerator, which is x squared plus x plus 1. And here's, we'll see what I mean. To do division, remember how to do that? Everything else you go right to left. Multiplication, addition, subtraction, you do right to left. Division, you do left to right. You take the term over here, x squared, divide that into that x squared. Well, x squared will go into x squared exactly one time. Then we multiply, just like we do with long division. 1 times x squared is x squared. And this is why I put this in. 1 times 0x is plus 0x. If you didn't have that in there, you might be tempted to put the plus 1 here, but no, it can't go there. You have to have it under like terms, and this then is a plus 1. Okay, now we subtract. Okay, I like to say change signs and add, but you don't have anything but positive signs here, so when you subtract these, they go to 0. Subtract these, they go to 0. So that gives you a remainder of 1 minus 0 is x. X minus 0 is x. That's your remainder. Well, how do you deal with the remainder? You put plus x over x squared plus 1. Now you don't need to put that 0x in there. Your remainder over your divisor is how you did that. I don't know if you remember back when you did long division, if you had a remainder, say you were dividing 7 into 9, 7 will go into 9 one time. 1 times 7 is 7. 7 from 9 is 2. It would be 1 and 2 sevenths. That would be your answer. You put the remainder over the divisor. Okay, so there's your answer. Well, then this integral here is now the integral of 1, which I'm just going to say is dx, 1 dx, plus the integral of x over x squared plus 1 dx. I just break this into two different integrals. This integral, that integral. And what's the antiderivative of dx? No u substitution required here. What's that? Anybody? X. You got it. Now, you might need a u substitution here. Let u equal what?
X squared plus 1.
Perfect. Then du is equal to 2x dx. Perfect. We don't want an 2x dx. We only have an x dx, so let's divide both sides by 2. Get rid of that 2. And now what we have here is plus 1/2 the integral of du. The 1/2 came out front, so that's just a du over u. So this will be, this looks weird because it has x's here and u's here. This is x plus 1/2 times what?
Absolute value of x squared plus 1.
You got it, okay? I'm going to put the u there because I already wrote it, but you're absolutely right. So this becomes x plus 1/2 the log of, now, you said absolute value of x squared plus 1. Well, look at that. Whatever value x has, when you square it, that's going to be positive or 0, but if you add 1 to it, it's going to be positive, okay? It can't even be 0. So we don't need the absolute value bars here. We can just put x squared plus 1. And then we can put our plus c out here. And we could, if we wanted to, the book probably does it, x plus the natural log of x squared plus 1 to the 1/2 power plus c. And if you wanted to, you could take it one more step and say x plus the square root of x squared plus 1 plus c. Those last two forms are not necessary, but all three of those are completely correct answers. WebAssign, of course, would only give you credit for one of them because it is a stupid program, and it can't interpret. Okay, the book left it just like that one right here. I figured that's how they would leave it, just like this. And that's absolutely correct. Okay. And they suggest, and it's always true, check your result by taking a derivative. If when you take a derivative you wind up with exactly what you started with, you knew you got it right. Now, that problem would take a little bit of effort to do. Now, I wish I knew how to erase all this. I don't. This Wacom, or the interaction with Wacom in PowerPoint and maybe through Zoom, I don't know. I can't get this to erase. So let's just see how they do this. I bet you it's very similar to us. Begin by using long division to rewrite the integrand. This thing here is equal to x squared plus 1. They didn't put the plus 0x in there. Divided into that, but they did have to leave a space here, okay? Because you can't subtract things that are not like terms. So that's what they did. And they wrote that answer as 1 plus x over x squared plus 1, which is exactly what we got. And then they did the integral of this thing, which would then be, that integral here would be the integral of this thing up here, dx. They're taking extra steps here, and that does get it to a clean page. There's the integral of 1 dx, which we did jump right to, plus, and then they skipped the u substitution. The harder part, they wrote the easy part down in 2 steps. The hard part they just skipped, and said that gives you this, okay? And it is. What they did is absolutely true. And when you do that, then you get integral of x dx is, the integral of dx is x plus 1/2 the log of x squared plus 1 plus c. Now they skipped the u substitution. If you can see how to do it without it, perfectly fine. Do it. To me, it's always easier to go on and do the u substitution and see. But some people don't like to, so if you don't want to, just don't make errors. That's the key. And that's the answer they give. And it said check the result by differentiating to see if you get that original thing, which is what I already said. All right, so that's example 5. Where do they go next? They skip example 6. So let's go back here. I apologize, my head is stuffing up on me. I'm going to need to drink a little something. When I was waiting for Zoom to open and getting all my PowerPoints done and all, I was eating almonds and I think I dried myself out. And then too, this weekend, like I was saying before, I had other things to do. Many of them were taking advantage of this beautiful weather we had to do some outside work, and I did that. So I think the pollen and stuff like that is also getting to me. So sorry that I'm having to take a break to get something to drink. So let's go back to our, unless there are any questions on this, go back to the whiteboard. Any questions? Okay. And let's clear this. Does anyone need that 4D, example 4D any longer? I hope not. Let's clear that. So let's do example 6. Let's see if I can read it this way. That's the integral of 2x over x plus 1 squared dx. Now that is a sort of slightly different looking kind of problem. Okay? Now, perhaps there is a way to do it straightforwardly. I would say go on and multiply out that denominator. Square that binomial. And that would be the integral of 2x over, and what is x plus 1 squared? Okay, square the first, twice the product of the two, and square the last. Sorry, I'm still congested. All right, now, still doesn't quite look all that promising, but let's see what we've got. Let's try our good old U substitution. What would you let U be?
X squared plus 2x plus 1.
I'm not sure this is going to work, but let's try it. And then our then dx is equal to, du is equal to
2x plus 2dx.
got it. Now, we don't have that up here, do we? Okay? And there's really not too much of a way to get it. Unless you did this. You put a plus 2 up here. Now understand this plus 2 is over all that times the dx. And then over here I'm sorry, a minus integral of 2 over x squared plus 2x plus 1 dx. Now you see what I did there. I added 2 over this here and subtracted 2 over that there and then split them up. This will give me exactly my integral of du, because that's what du is, over u, because that's what u is. But now I have a problem, don't I, Houston? Okay? And this will be minus the integral of 2 dx. And I'm going to be really sneaky about this and change this back to x plus 1 squared. Okay? Now, and you might say, why would you do that? Well, let me explain. Let's first do this one. What's your integral of this one right here? Natural log of absolute value u, right? We're going to hold off our plus c until the end, because no reason to put a plus c for this one, plus c for that one. Add them all together and they're still a constant. Okay. Here, the u substitution would be a different. So are you okay with me using u again, even though it's going to be a different substitution? Or would you rather I use a different letter like v or something else? You tell me.
You can use u.
Okay, thank you. Okay, let u equal, in this case, we're doing the innermost part of the complicated part. The innermost part is the x plus 1. Okay, then, it's not writing my e's well, du is equal to what? Anybody? If u is x plus 1, what's du?
1.
1 dx, right? Now, up here we have a 2 dx. Well, what I could have done was pull this 2 on the outside and made that just a 1 dx. Okay? And that's okay too. So what does that give us? That would be a minus 2, and this would be a du, that's the dx here, right, over u squared. Okay? Now I'm going to write that a slightly different way. Now, I'm going to go on and put what this u is so we don't have so many u's out here. This u is indeed this one. That's absolute value of x squared. Oh, you know, we don't need that, do we? I'll tell you why. Whoa, I erased more than I wanted to. Okay. What was that u here? That was the x plus 1 squared. That's what that was, right? Well, guess what? X plus 1 squared is never 0, and it's never negative. Oh, wait. I guess it could be 0, couldn't it? If x is equal to negative 1. Oh, boo hiss. Okay. But it can't be 0. I mean, it can't be negative. So I think you do have to put in here, where is my pen? There it is. Okay. X plus 1 squared, because that's what this thing here was, x plus 1 squared. That can't ever be negative. Now, of course, x can't be negative 1, because in our original problem it can't be negative 1, because that would be negative 2 over 0, and you can't do that. So it's already given x can't be a negative 1. So not going to worry about that. It just, any other x is going to make that positive. Okay? Now, we got that substitution made. Now let's go here. Where in the world is my pen now? Oh, there you are. Okay. Minus, now, what happened to my integral sign? I don't know. I don't think I left it off, but maybe I did. Okay, this will be minus 2 times the integral. I'm going to rewrite this as u to the minus 2 du. Isn't that legal in most states? So the first part is still the log of x plus 1 squared. And what's the antiderivative of u to the minus 2 du? Where is, there it is. Okay, minus 2, what's the antiderivative of u to the minus 2? Well, that's a power rule, right? You add 1 to this and you get a minus 1, divide by that minus 1, which basically is just going to make that a plus, and now do the plus c. Incorporate it all. Now let's plug back in and see what we've got there. We've got the log of x plus 1 squared plus, now what is u? In this case is x plus 1. So that would be plus 2 over x plus 1. No absolute value bar needed there, plus c. There is our solution. Now, this, about the most complicated one we did, and of course they didn't do that one on the PowerPoint, and they do that sometime. So we have, now of all the times they've not done the power rule, they're doing it this time. You can write this as, and this would drive me crazy if I were doing it in WebAssign, you could take this 2 and move it out front 2 times the log of x plus 1 plus 2 over x plus 1 plus c. That's their answer. Okay. Now, they did do it a slightly different way, and maybe you like the way they do it better. It's perfectly legitimate. I just thought this followed the pattern we've been doing a little bit more closely. But we did have that trick up here of adding a 2 here and subtracting a 2 there, and that gave us the right answer. What they did was use the x plus 1 as your denominator as the u substitution here, and then they had to fiddle around and get what 2x is, which is just as good, probably just as few steps, maybe a few more, but it's another way of doing it. So if you like the way the book did it, by all means that works too. All right, now I think that pretty much is what we've got until we get to these guidelines, which are coming up next. However, there is something they have at the top of the page here they don't put on the slide set. It says, as you study the methods shown in examples 5 and 6, be aware that both methods involve rewriting a disguised integrand so it fits one or more of the basic integration formulas. Okay? It says throughout the remaining sections of chapter 5 and then later in chapter 8, much time will be devoted to integration techniques. To master these techniques, you must recognize the form-fitting nature of integration. In this sense, integration is not nearly as straightforward as differentiation. Differentiation says, here is your function, what is the derivative? Okay? Whereas integration is more like, here is what you get after you take a derivative, find out what function that was. In other words, here is the answer, what was the question? Okay? And that can sometimes be a little daunting. But you have to sort of start thinking, and that's, I think, maybe one reason, maybe they not conscious, of why they call them antiderivatives. You have to think backwards. Just like the power rule. You add 1 to this and then take that denominator and divide by it. Okay? You're doing things backward from what you did with derivatives. Okay. So let's go and look at these guidelines they give us. Okay? Let's go back to our 5.7, back to current slide, and here's the guidelines. The following guidelines can be used in integration. Number 1, learn a basic list of integration formulas. How do you learn that? Do I sit down and memorize? No, I don't memorize. I don't like memorize. Now, if you do, you can do that. But frankly, use them often enough, you get to know them. Get to know them, okay? Learn them by using them. Did you ever sit down and memorize your name? I bet not. You just had everybody calling you that your whole life, and you knew it was your name. Well, same thing here. Use them over and over again until they become yours. Learn that basic list of integration formulas. Find an integration formula that resembles all or part of the integrand, and by trial and error sometimes, find a choice of u that will make the integrand conform to the formula. Okay? Now, to me, I have a simpler way of doing that u substitution there. Look for the innermost part, the most complicated part of your formula. Okay? Of your integrand. Number 3, when you cannot find the u substitution that works, try altering the integrand. You might try trig identity, multiplication and division by the same quantity, or as we just did, addition and subtraction of the same quantity. Remember, I added the 2 over that denominator, and then I went back and subtracted the 2 over that denominator and did those in separate integrals. This one gave me one I could use as u substitution. This one gave me one I could use a different u substitution. Or long division, whatever it is, be creative. Now, I want to mention this to you as well. I feel like I'm jumping the gun, but when they say learn the basic list of integration formulas, guess what? You can go to the back of the book or even the front of the book or find some integration tables and see if you can match the one you've got with something that looks like theirs. Okay? We'll be doing that when we finish chapter, I believe it is 9 or 8, the one they were talking about. If you have access to a computer software program that will find antiderivatives symbolically, use it. I don't have that, but if you do, you can do that as well. Always check your result by differentiating to see if you get that original integrand. Okay, those are the rules. Here's example 7. Solve this differential equation. Now, to me, this is jumping the gun. That should be a different thing. But these are really simple differential equations, so here's what we're going to do. First thing I'm going to do is, they call this a differential equation. In one sense, this is a derivative equation, because that's a derivative is equal to something over here. Now you can do what I'm about to do because everything that's over here is in terms of your independent variable. If you had any y's in here, you can't legitimately do exactly what I'm going to do now. So they call it a differential equation, so what I suggest, write it in differential form. What do we mean by that? That means you write the dy by itself is equal to 1 over x log x dx. So write it in differential form. You split the derivative, write the dy on one side, dx on the other side. Now you have something we can integrate both sides, because this one has only y's, this one only x's. That's why I said this only works when the right hand side is only in terms of your independent variable. Alright, now I can do this one. What's the antiderivative of dy? Y. But I'm not going to do a plus c for that one. Let's wait and do 1 plus c for all of them. Okay. Now, what in the world do we do with this? It's a rather complicated looking problem. What do you think is the most complicated? Okay, what's complicated there, everything's in the denominator. What's the innermost part of that denominator? This my little rule sort of falls apart here. It's here's your u substitution, let u equal log x. Now why would we do that? Let's see what the then tells us. Du would then equal what? What's the derivative of log? Log x? Oh, come on, we've been doing antiderivatives with it. Derivative of log x. Go to the front inside cover of your book. Okay? That cardstock page at the very beginning, the basic differentiation rules. There it is, number 9. D by dx of log x is 1 over x. They don't have it quite in that way, but what it is. So your du here would be, I've got to get on the right pad here, du would be 1 over x dx. That's it. Well, what do we have? 1 over x dx, that's your du, and this is your u. So what do we have? We have the integral of du over u. Now this is a rather strange one, I'll admit that. What does that become? You've done it several times today already. Log of absolute value of u. Now here we can go on and put our plus c in there. That we've taken that second integral. That incorporates the plus c we had from the integral on this side. Okay, they're all added together. Well, now we go back and do what this is. This will be y is equal to the log of, but what was our u? It was the log of x. So it's the log of absolute value of the log. I don't know why I do that, but I do it sometime. When I go to write log, it becomes an H looking thing. I don't separate. Log of absolute value log x plus c. Now, there's no simplification here at all. Okay? There aren't any rules for logarithms of a log of a log. That's what it is. Okay? And let's see what they got, and that's exactly what they got. Y is equal to the log of absolute value log x plus c. Exactly that. So I can't erase this. Sorry, I can't. Let's see what they do. The solution can be written as an indefinite integral, and what they did derivative of the integral of a derivative is, this is fundamental theorem of calculus part 2, or second fundamental theorem of calculus, however you want to say that. That gives you this is equal to the integral of this side with the dx there. I think it's better to go and move the dx, write it in differential form. That puts the dx there, and then integrate both sides like we did. It gives you the same answer. And because the integrand is a quotient whose denominator is raised to the first power, that's a weird way of saying the because here. The integrand is a quotient whose denominator is raised to the first power. What they're saying is true, but that's a weird way to express it. It said you should try to use the log rule. I'd say just use a u substitution. Let u equal log x. And when you do that, it says there are three basic choices for the u. The u could either be x, which isn't going to do, x log x, that's going to be a pain in the neck to do a dx for that one, and they don't fit the thing. The obvious thing to do is let the u be log x. And when you do that, you get derivative of u, or u prime, is then 1 over x dx. Why they changed their way of doing it, I don't know. And then that gives you the integral of du over u. And that is another way of writing it. That's perfectly fine. And that is the log of the log. And now they do the u substitution. Let u equal log x. I would have done it right here. They do this first and then do it here. Perfectly fine. It's correct. And that would be log of u plus c, and that would be log of log x, absolute value of log x plus c. Okay. Any questions on that? A rather bizarre problem, but one that has a rather clever solution. All right. So the solution is y is equal to log of log x, absolute value of log x plus c. And you have to have absolute value bars there because remember the log of anything less than 1 is negative. So you have to have, because there's no guarantee that the x is not between 0 and 1. If it is, that's going to be negative, so you have to have the absolute value bars there. All right. That was example 7. Now we're ready to move to page 360, integrals of trigonometric functions. Okay. Now, here's example 8. Without any further ado, they do this. Now, first thing I think of when I see something like that Is tangent x a derivative of something? The perfect derivative of something? And the answer is no, it's not. Okay. Well, since you rule that out, you can't just go straight forward and do an antiderivative because there is no function whose derivative is tangent x. So then excuse me, I've got hiccups now. Fall back on what I said earlier. If I can't see any obvious thing, I rate everything in terms when I've got trig functions in terms of sines and cosines. And does anyone remember what tangent is in terms of sine and cosine? Please say yes. Otherwise, I've got to get in touch with your trig instructor. Oh, that would be me in three cases. No, two cases anyway. What is tangent? Sine over cosine. Now, that looks like it got more complicated, doesn't it? Except that now I can see a u substitution here. The most complicated part of that is your denominator. So let u equal cosine x. Then, anyone tell me what the then will be? What's the derivative of cosine?
Sin x dx.
No, minus sine x. The antiderivative of cosine would be positive sine. The derivative of cosine is minus sine. Watch those negative signs. They're only there. Excuse me. Excuse me. Not sure why that came on. Thank you. Uh, it is cooler this morning than it has been other mornings. I don't have the ceiling fan on. The room's just cool. Okay. Uh, Probably I should have on long pants. Oh, I shouldn't have said that, should I? You didn't know that I've been teaching your class in shorts and sandals. Okay. Never would have done this in the classroom, but I'm at home now. You only see the top part. Okay. The If u is cosine x, du is minus sine. Where in the world is my pen? There it is. Sine x dx. Okay. Well, we don't have a minus sine x dx. We have a sine x dx. So what we're going to do is multiply or divide both sides of this equation here by minus 1. So that's going to move the minus over here. So what this becomes is then minus the integral of, now the sine x dx is minus u, so I put the minus on the outside, du, so I put the du in here over, and your u is here. Oh man, that's something we've seen before, isn't it? What would this be? Come on.
Natural log.
Yeah, of u. Natural log of u minus the natural log of u. Ooh. Okay, I have to. There we go. We have to put the absolute value bars in there because, well, we just do. And we'll go on and put our plus c here too. That's fine. So now we plug in what that is, minus the natural log of, and what was our u? Cosine x. But cosine x can also be negative, so you have to put the absolute value bars there and put plus c. Okay. So, this is a little problematic here because x can't be any half pi. Remember, your cosine is 0 at your half pi's, so basically you really need to identify what your domain is. And if you use the domain to be, cosine could be 0 because cosine of 0 is uh, 1. So that would be okay. So you could have anywhere from 0. Uh, Actually, let me think about this. I'd say from minus pi halves to pi halves. That would be a good region to do because cosine is positive in between minus pi halves and pi halves. And that would not bother your tangent at all because tangent's not defined anywhere but minus pi halves to pi halves. Well, on that an interval like that. So if you restricted it to minus pi halves to pi halves, this makes sense and this makes sense. And you could lose the absolute value bars there. I think the book probably keeps them, and yes, they do. So let's see how they do it. This integral does not seem to fit any formula in the basic list. We didn't look at the list, but it doesn't. So, however, by using the trig identity, you get tangent is sine over cosine. Oh, I know what I was going to do. Let's go up here for a moment. We could have done this, and I'm sorry, the book I don't think will do it, but I'm going to do it. This could be the log of absolute value cosine x raised to the minus 1 power plus c. Well, what's that? That's the same as the log of absolute value, well, 1 over, because this is the absolute value of cosine x. Okay, well, plus c. That is also the log of absolute value secant, because 1 over cosine is secant. And again, you could go back to what I was saying before, just to find that to be x has to be between minus pi halves and pi halves. Neither one of them, because that won't work for tangent. It won't work for secant either. So, or it would make secant, well, yeah, it won't work for them because it would be going to infinity. And secant is never 0. It's always positive in between minus pi halves and pi halves. So that would be a legitimate answer, just like we got before. The book I don't think is going to go that step. They're going to leave it just like we did. Integral does not fit, so therefore we do this. And when we do that, you see derivative of cosine is minus sine. So let u equal cosine, and then that would be that. Well, they like to put the minus here and there. I like to, at this stage, just make it. See, they don't write the du's the way I'm used to doing it. Minus du, so put the minus here, just have a du there. Seems like to me this just makes it more complicated, but if you like it better, you can. And see, they finally do it here, which is fine. And that would be, and why they put u prime rather than du, I don't know. And that's minus log of absolute value u plus c, and that's minus the log of cosine, absolute value cosine plus c. And they leave it like that. All right. How are we doing on time? Yeah, we got some time. We go to 11:40. We have 8 minutes. So let's look at these integrals. Wait. That was example 8. We haven't done example 9. So let's us do example 9. That probably is going to run us out of time. But let's try it. Let's go for the whiteboard and clear what we got. Okay. Oh, this is a bear. Okay. The the integral or antiderivative of secant x dx. Now, frankly, I go to the table. Okay. I can't remember if we did this before. I don't think we did, but if we did, it's a pain in the neck. And it happens to take a really bizarre set of circumstances here. And here's what you do. And there's nothing, I can't think of anything else to do but say, this is the trick. It's not a procedure, it's not a method, it's a trick. And what we're going to do is write down the secant x, if I could write it, and I'm going to multiply and divide this by secant x plus tangent x. And you might think, why in the world would you ever think of doing that? I wouldn't. I've just seen it happen often enough. I know that's the trick. It's a trick. It's nothing, nope, that's not tax, it's tangent x. Nothing but a trick. Okay? Now, doing that, see what you get. That would be the integral of secant times secant is secant squared x plus secant x tangent x. Pen is not writing well. I'm in a hurry because I know we're running out of time. Over secant x plus tangent x. Okay. Goodness, it's not writing. Okay. dx. This drives me nuts. Okay. Now, let u, now I know the numerator looks more complicated, but that denominator is in the denominator. That makes it complicated. Let u equal secant x plus tangent x. This is just amazing what's going to happen here. And maybe you've already figured it out. Okay? Then, let's do a du. Does anyone know what the derivative of secant is? Derivative of secant is secant x tangent x. Now, I hope you remember what the derivative of tangent x is. We had that in an earlier problem. That's secant squared x. And then you have a dx out here. Well, looky here. This thing here is exactly that thing there. It's just in reverse order. But addition is commutative, so you can change. So basically what this is the integral of du over u, and this is absolute value, log of absolute value u plus c, which is the log. And what is u? That denominator, absolute value secant x plus tangent x. Plus c. That's their answer. You'll see the integral of a secant x is the log of a secant x plus tangent x plus c. Now, there's no handy dandy way you can simplify this very much, except note secant x is only defined to be, it can't be, you never can take a half pi there. So if you define secant x be between minus pi halves and pi halves, that's fine until you get down here, and that would be positive between minus pi halves and pi halves, but this is negative, very negative in some places, between minus pi halves and 0, and positive after that. So the only way you can make this lose the absolute value bars if you define it between 0 and pi halves. You can include 0, but don't include pi halves. But they left it like this, and that's their answer. Okay, now how are we doing? 2 minutes. All right. Sorry I rushed that, but I knew we were running out of time. Well, why did I do that? It doesn't matter. Here's what I meant to do. Okay. The integrals of the 6 basic trig functions are summarized below. The antiderivative of sine is minus cosine. Remember that from before? Because the derivative of cosine is minus sine. Okay. The antiderivative of cosine is sine because the derivative of sine is cosine. Now, of course, these have the plus c's. I'm leaving those off. The antiderivative of tangent is minus log of cosine, absolute value of cosine. Now this, I don't know what that line is there. It's spurious. It doesn't belong there. Sometimes it just pops up here. It's not there. That's not another absolute value. It's just not there. Okay. I don't know why it looks like it's there. Or you could call this the log of absolute value secant u. That's the other way you could solve that. Minus a log of absolute value cosine plus c, or the log of absolute value secant u plus c. Cotangent, very fairly similar, except now you lose the minus sign. It's the log of sine. And the reason for that is if sine is your denominator, which it would be, the derivative of sine is cosine, not minus sine. So you don't need, it doesn't have the minus sign. Do I memorize these? No, I'll look them up if I need them. And secant, we just did it, is the log of absolute value secant u plus tangent u plus c. And similarly, the log of the integral of cosecant u is minus the log of cosecant u plus absolute value of cosecant u plus tangent u, cotangent u plus c. Now, do I trust my memory to get the signs, the pluses and minuses in the right place? No, I look them up, and I suggest you do too. All right, I think that's probably run us out of time. We're right now at that time, so we're going to start next time with example 10. I can't pick up my pencil. Okay, we'll start with example 10 on this page, page 361, and just got those two examples to do and we'll be through. So homework exercises here would be any of the odds 5 through 27. They're all at Calc Chat, 9's at Calc View. 29 or 31, they're both at Calc Chat, 29's at Calc View. Any of the odds 33 to 41, they're all at Calc Chat, 33's at Calc View. 43 or 45, both at Calc Chat. 47 should be at Calc Chat. 49 should be at Calc Chat. That's the slope field. We did that sometime or another, but don't worry about it if you don't want to fiddle with that. Any of the odds 51 to 57, all at Calc Chat. 55 is at Calc View. 59 should be at Calc Chat. It says you need a graphing calculator. I think you can probably get by without one, but see if you can. Either 61 or 63, they're both at Calc Chat. Either 65 or 67, they're both at Calc Chat. 67's at Calc View. Either 69 or 71, they're both at Calc Chat. 69's at Calc View. 73 or 75, they're both at Calc Chat. 73's at Calc View. Okay. I think you can do 77. It should be at Calc Chat. I think you, yes, it's out of time.
Is this the homework that's gonna be graded, or this not like that's not the assignment?
Okay. What your assignment is, okay, pick a homework problem, any homework, not all these, just pick one and submit it, and that's what I grade. Now, I prefer, if you're having any difficulty finding the answers to these, and it may be more than one, send me those, because then I'll know, let's do that in class. And in fact, I'd like you, when I start class, I always say, any questions, problems, issues, anything. Yes, could you do number 45 on this page? So I'd rather you pick one that you're having trouble getting the right answer. Okay, you don't know how they got the right answer. You went to Calc Chat, you saw that's how they did it, but you don't know why they did it the way. Maybe it was even at Calc View and you look at that and interact with it and you still don't know why, those are the ones I want you to send me. Okay? If you're not having problems with any of them or you can figure out how to get them, send me any one. If you're having difficulty with several, send me those several so we'll know to do several like that in class. Does that answer your question?
Yes, sir. And I know a couple, a couple of the well, other kids in our class don't have books. Could you just show them the problem? I don't know how they gonna get it. I know that's probably gonna be a problem for them.
Okay.
I know they all got the book.
Okay. Not even ebooks, huh?
I know last time, yeah, ain't nobody have the book.
Oh,
I
really?
have mine, but I have trouble going through it.
Okay.
I have the ebook.
Okay. Andy has the ebook. How about Jordan and Brandon?
I got it.
Jordan does. How about? Oh, you all have either a book or an ebook, so they all have the problems available to them. So yeah, I think at one time not all the ebooks were working because the codes or class keys or something like that. It makes it such a pain in the neck. They make things so complicated, but I'm glad y'all got them now. So yeah, do any of these, and let's just stop them there. Well, let's see. No, I think we can go on. Let me go. 77 should be at Calc Chat. 79 should be at Calc Chat. And then any of the odds 81 through pages 362 to 363. I'd say 81 or 83. Stop there because the rest of those are your trig functions. We'll do that last couple of examples, then I'll give you the trig problems to do. Okay? Now, since the question was asked, and if some of you think, well, I haven't been turning in homework exercises, if you want to go back and do some for any of the earlier weeks, you certainly can. Just let me know when you send me a homework problem. Two things I'd like you to be sure you have on there. Number one is your name. A lot of times when I catch it that your name's not there, I still have the email or the message or whatever up there, and I can figure out who you are. But if I printed off a bunch of these together and then suddenly I look at them and say, wait, this one doesn't have a name, whose was that? I don't know. So please put your name. And then also, if you're doing it for a past week, then put week 2, week 3, week 4, week 5, or
So you
week 6.
just want one problem.
One problem is all I need. They just require some sort of turn in. So one problem. Now you don't have to do it. It's just basically a thing there's no points for it. What it does give you though is at the end of the term, if you happen to have a grade that you're not quite high enough to round up to a C or a B or A, and you're just missing that, I'll look at the grade sheet and you've submitted more than you've had blank. In other words, you've submitted more homework than weeks gone by without homework, then I'll consider bumping you up that half point or whatever it takes to get you that next grade. If you had an 86.5, guess what? That's still going to be a B. Okay, a half point is going to make it 87. that's all you're going to get is a B. It's only if you wind up in that little narrow range that you may happen to be so close but not quite there. If you turn in more homeworks than you've left blank, I'll bump it up. Okay?
Okay, so and the test was Wednesday.
Okay, now that's the thing I was going to say. We're two examples short of finishing the chapter. Do you want me to go on and put the test out there now, or do you want me to wait till we finish those two things on Wednesday? It's up to you. I think I asked this last week, and you said,
I think it'd be better if you turn it in, do it today, and then whatever problem we don't get right, you just turn it in by Wednesday.
okay, yeah, well, you don't have to turn it in the next day anyway. You'll have 1 week at least to turn it in, and you can take more time if you need it. Now, here's one thing about the test. I checked it this morning. I'm going to skip 5.8. The last when I made out this test, I was thinking we were going to do 5.8, but we got to move on, folks. So the last problem is one I'll make optional because it's based on 5.8. I'll make that an optional problem. If you do it and get it right, you get a bonus point for it. If you don't do it or get it wrong, you don't lose any points for it. So I'll try to put it out, but it's going to be sometime after 4 o'clock today before I have a chance to do it. Probably more like this evening, because I've got another class coming up right away and then another one right after that. So it'll be sometime this afternoon or evening before I'll put it out there. And I'll put it out both under what now says week 6 assessment. It will then say test, chapter 5 test in parentheses test 1. So, and then I'll also put it under Blackboard message. I'll put it out there both ways. Okay? All right.
Okay, sir.
All right. Any other questions before I shut down the sharing? I'm sick and tired of sharing. Okay? Gonna stop the share. And unless you have any other questions, I'll go on and end the meeting. Any questions?
What you said 5 point. There was a bonus question. What page is that on? I was trying to write it down on my iPhone, so I won't forget.
Okay, on your test. On your test, the last question is based on 5.8. If you want to try doing it, you certainly can. If you don't want to do it, you don't have to. If you get it right, it's a bonus. If you get it wrong or leave it blank, it doesn't cost you. It's totally bonus. Okay, but that'll be when you see that test, and that'll be sometime this evening. That last problem is like that. Okay, good question. Any others? All right, take care. Yeah.
Is that the Wednesday?
No, 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 no. The test won't even be officially out there. I'll give it to you today, but until we finish 5.7, that's when the clock starts, and I always give you at least a week. So you have time to ask me questions in class one day. But again, guess what? If you need more time than a week, you can have it. Just, I don't want you having two tests out at once. So be sure you get this one done before we're ready for the next test. And the next test is going to be based on chapter 7, which is a fairly, I'm sorry, we skipped, let me make sure I'm saying that right. Uh, yeah, chapter 7. And chapter 7 is um, applications of integration. That's going to take us a while to do. I can't remember how many sections there are to it, but there are quite a few. So yeah, you got plenty of time to work on it. Don't dawdle. There are 7 sections in chapter 7. So yeah, we're going to be a while before we're ready for the next test. So you got plenty of time, but get it done as soon as you can. But okay, does that answer your question? All right,
Yes, sir. It does. Thank you.
all right, good deal. I'm going to end the meeting then. We'll see you on Wednesday, okay? Bye bye.